Welcome friends to my lecture on solution of second order differential equations by changing independent variable. Now we are going to discuss another method. Sometimes this method is found to be very useful, and in this method we change the independent variable. So far the differential equations that we are considering, they are of second order linear differential equation with variable coefficients where x is the independent variable. So in this method we will change the independent variable from x to say another independent variable, that is z. So let us consider a linear differential equation of second order, that is by double dash plus p y dash plus q by equal to r, where p, q, r are continuous functions of x on some interval I. We will be changing the, as I said, we will be changing the independent variable from x to z. The relationship between x to z will be found from the fact that the changed equation it becomes readily integrable. So once we have that aim in mind, that the changed equation has is readily integrable, from there we shall be able to derive the relationship between x and z. So let us see what we do. Since x is related to z, we can write dy by dx equal to dy by dz over into dz by dx, and d square by dx square. If you find d square by dx square, then d square by dx square will be equal to d over dx of dy by dx, which is equal to d over dx of dy by dz into dz by dx. So differentiating this product of functions of x, we shall be having d over dx of dy by dz into dz by dx plus dy by dz into d square z by dx square. Now this can be further expressed as d over dz of, because z is a function of x, we can write it as this, into dz by dx into dz by dx plus dy by dz into d square z by dx square. So this will be equal to d square y over dz square into dz by dx whole square plus dy by dz into d square z by dx square. So the second derivative of y with respect to x is equal to d2 y over dz2 into dz by dx whole square plus dy by dz into d square z by dx square. Now substituting these values of by dash and by double dash in the equation 1, in this equation 1 we shall have this expression d square by over dz square into dz by dx whole square plus d square z by dx square plus p dz by dx into dy by dz plus q y equal to r. Okay. So now let us let us write this equation in the form d square by over d, in the standard form, d square by dz square plus p1 dy by dz plus q1 by equal to r1, where we write p1 for this expression d square z by dx square plus p dz by dx over dz by dx whole square, and q1 we write for q over dz by dx whole square, and r1 denotes r over dz by dx whole square. So these p1 q1 r1, p1 q1 r1 are some functions of x, and they can be easily expressed as functions of z by the relationship between z and x, which we have yet to establish. So now what we do is, let us discuss various possibilities which will give us a function of z, z as a function of x, and with those possibilities we shall be able to integrate the equation 2. So the first possibility is that let us equate q over dz by dx whole square. Q over dz by dx whole square is q1. So let us equate q1 to a constant. So if we do that, so what do we have? q1 equal to q by dz by dx whole square. suppose it is some constant. Then if it so happens that P1 also becomes a constant, if P1 also becomes a constant, then the equation 2 will be a linear differential equation of second order in the independent variable z, the dependent variable y with constant coefficients. And we have seen earlier how we solve a second order linear differential equation with constant coefficients. So if the function, if z is a function of x in such a way that q over dz by dx whole square is a constant, then if P1 also becomes a constant, the equation 2 is at once integrable. So this is one possibility where we can find the general solution of equation 2. Now since z is quite arbitrary, it can be chosen to satisfy any assignable condition. So one condition that we put is that q over dz by dx whole square is equal to a constant. Let us look at other possibilities. In the other possibility, what we do is we choose z in such a way that the coefficient of dy by dz in the equation 2 vanishes. So coefficient of dy by z in the equation 2 is P1. So let us put P1 equal to 0. So if P1 equal to 0, we get d square z by dz square plus P dz by dx equal to 0. Okay, so let us say, suppose u is equal to dz by dx, then this equation, the above equation can be expressed as du by dx plus p into u equal to 0. We can separate the variables u and x are now let us integrate. So integrating both sides, we have ln u equal to minus integral p dx, okay, or u equal to e to the power minus integral p dx, okay. So thus dz by dx is equal to e to the power minus integral p dx. Now integrating again with respect to x, we get z as integral e to the power minus integral p dx dx. So if we put the coefficient of dy by dz, that is P1 equal to 0, we get z equal to integral of e to the power minus integral p dx dx. And after that, if q1 with this choice of z as a function of x, if it so happens that q1 becomes a constant, then it is a second order linear differential equation with constant coefficients. It will be d square by over dz square plus a constant times by equal to r1. So it will be a linear differential equation of second order with constant coefficients, and therefore we can solve it. We can find the general solution of this equation. Now the other possibility is that suppose q1 is a constant divided by z square, then z square times d square by dx dz square plus a constant times by will be equal to r1 times z square, and so we will have Cauchy-Euler equation, and we know how to solve Cauchy-Euler equation. So we can again get the solution of this differential equation. So if P1 is taken equal to 0, and after that P1 equal to 0, we get z as a function of x. With this choice of z as a function of x, if q1 either becomes a constant or q1 is a constant divided by z square, then we can find the general solution of equation 2, and hence we can find the general solution of equation 1. So that is one more possibility, and so we can see here if the equation 2 will reduce to this form. If the q1 comes out to be a constant or a constant divided by z square, the equation 3 becomes readily integrable. Now let us see when we put q1 as a constant, okay. Say suppose q1 we take as some constant a square, okay. We just want z as a function of x, so this constant can be chosen according to our requirement. So we will be choosing q1 equal to a square. So then aq upon dz by dx whole square. This is equal to q1 and q1 is a square. So, we shall have dz by dx equal to q upon a square or root q divided by a. Okay, or we can say z is equal to 1 upon a integral root q dx. So, we will get z as a function of x. Now, so this is what we will get, and the equation will reduce to d square by over dz square plus p1 dy by dz plus a square by equal to r1. If p1 is a constant, then the equation can be easily integrated, okay, because it will be a linear differential equation of second order with constant coefficients. Okay. Now, let us see some examples on this. Okay, so let us consider the equation given in example 6. First, we will write this equation in the standard form. So, the coefficient of d square by dx square will be made unity, which means that we will divide the equation by x to the power 6. So, we shall have by double dash plus 3 by x by dash plus a square by x to the power 6 into y equal to 1 by x to the power 8. Now, so when we compare this equation with the standard form, we get p equal to 3 by x, q equal to a square by x to the power 6 and r equal to 1 by x to the power 8. So, let us first explore the possibility when we put q as a constant. Okay. So, let us put q as a constant. So, let q be equal to some constant, say, okay, let us take it as 1. Okay. Then what we q by dz by dx whole square be put as a constant. So, wait, I think, wait a minute, sorry. So, let us let q1 be equal to, q1 is equal to q by dz by dx whole square. Okay. After we change the variable from x to z, we get this q1. Okay. So, after we change the variable from x to z, we will get q1 as this. So, this you let us put as equal to, this is equal to a square by x to the power 6 into 1 by dz by dx whole square. Let us put it as a constant, say 1. Okay. We can take any value of the constant. If you do not take here 1, you take some other constant, then the relationship between x and z will be changed accordingly. So, r dz by dx whole square equal to a square by x to the power 6, okay, which implies that dz by dx equal to a by x cube. Okay. And this gives you, when we integrate with respect to z, we get z equal to a x to the power minus 2 divided by minus 2. Okay. So, this is a upon minus a upon 2x square. Okay. Now, let us find the value of p1. p1 equal to p dz by dx plus dz by dx whole square, d square z by dx square upon dz by dx whole square. So, p is equal to 3 by x, dz by dx is a by x cube plus d square z by dx square we can find from here. So, d square z by dx square be differentiated once more. So, this is a times x to the power minus 3. So, we have minus 3a x to the power minus 4. So, minus 3a by x to the power 4. So, we get minus 3a over dz by dx whole square, which is a square by x to the power 6. Now, here we have 3a by x to the power 4, here minus 3a by x to the power 4. So, this is equal to 0. So, when q1 is assumed as a constant, which we have taken here as 1, P1 also comes out to be a constant which is 0. Okay, so we have the equation in the independent variable z as d square by over dz square plus P1 dy by dz plus q1 into y equal to r1. Okay, this becomes d square by over dz square plus q1 we have taken as 1. So y and r1 is r over dz by dx whole square. So r1 is 1 over x to the power 8 r1 divided by dx whole square. So divided by a square over x to the power 6. So we get here x to the power 6 over a square. So we get here d square by over dz square plus y equal to 1 by a square x square. Now we have to change the variable independent variable from x to z, and the relationship is z equal to minus a by 2x square. So 1 by a square 1 by x square is 2z over minus a. Okay, so this is 1 by a square 2z over minus a. 1 by x square equal to 2z over minus a. Okay, so this will be minus 2z over a cube. Okay, now this is a second order linear differential equation with constant coefficients. So we can write the complementary function for this. Here the auxiliary quotient will be m square plus 1 equal to 0. So the roots will be complex conjugate m equal to plus minus I. So complementary function will be c1 cos z plus c2 sin z, and z we see is equal to minus a by 2x square. So c1 cos minus a by 2x square plus c2 sin minus a by 2x square. Cos minus theta is equal to cos theta, sin minus theta is minus sin theta. So we can write it as c1 cos a by 2x square, and here minus c2 sin a by 2x square. Minus c2 can be replaced by another constant, say c2 dash, and we can write c1 cos a by 2x square plus c2 dash sin a by 2x square. So that is okay. Now a particular integral let us find. So this is by px by pz. Let us first find. Okay, let us find by px. By px will be 1 over d square plus 1. 1 over d square plus 1 acting on minus 2z by a cube. So this is equal to minus 2 by a cube 1 over d square plus 1 acting on z. Okay, now this is a polynomial, z is a polynomial of degree 1. So 1 over z plus d square plus 1 we shall expand as in the form of binomial expansion. So minus 2 by a cube 1 plus d square raised to the power minus 1 operating on z. When we write binomial expansion for this, we shall have 1 minus d square plus d4 minus d6 and so on, but the second derivative of z is 0. So we will get minus 2 by a cube 1 minus d square plus d4 and so on operating on z, which will give you minus 2 by a cube d square z d4 z all are 0. So we have minus 2z by a cube, and z is equal to minus a by 2x square. So this is minus a by 2x square. So this will give you 1 by a square x square, and thus the general solution is y equal to ycx plus ypx. This is ycx and this one is ypx. So, we take the sum of the two and write it equal to y. So, that is the general solution in this case. Now, let us discuss one more problem on this to make it more clear. So, let us take up another problem here. In the example 2, we are given the equation x d square by dx square minus dy by dx minus 4x cube by equal to 8x cube sin x square. So, again we divide the equation by x to make the coefficient of by double dash unity. So, we shall have by double dash minus 1 over x by dash minus 4x square into y equal to 8x square sin x square. So, here p is equal to minus 1 over x, q equal to minus 4x square, and r is equal to 8x square sin x square. Okay, so again we try the method where we put q1 as a q equal to a constant, q1 equal to a constant. So, after we change the variable from x to z, we get the equation d square by dz square plus p1 dy by dz plus q1 by equal to r1. So, here q1 is qy dz by dx whole square. So, let us put q1 as a constant. Say q1 will be equal to minus 4x square upon dz by dx whole square. So, q1 we can take as a constant. Let us take the constant as minus 1 to, then it will be simple. So, let us take q1 equal to minus 1, then dz by dx whole square will be equal to 4x square. So, which will give us dz by dx equal to 2x. One can take dz by dx equal to minus 2x also, that will give you other relation between x and z. So, the equation will be changed accordingly. So, we are taking positive here sign here. So, dz by dx equal to 2x, this gives you z as x square. Okay, so that z as x square. Let us find the value of p1. So, dz by dx is 2x, p here is minus 1 over x, and d square z by dx square is 2. dz by dx whole square is 4x square. So, again this cancels with this, minus 2 plus 2 is 0. So, we get p1 equal to 0, and thus the equation 1 reduces to d square y by dz square, p1 is 0, q1 is minus 1. So, minus y equal to r1. r1 is r over dz by dx whole square. So, 8x square sin x square divided by dz by dx whole square, which is 4x square. So, we shall have 2 sin x square. Okay, so complementary function here is this is auxiliary equation is m square minus 1 equal to 0. So, m is equal to plus minus 1. So, both the roots of the auxiliary equation are real and distinct, and therefore, we will have c1 e to the power z plus c2 e to the power minus z, and z is equal to x square. So, c1 e to the power x square plus c2 e to the power minus x square. Now, here this in order to find the particular integral, the right hand side of this equation which is linear differential equation with constant coefficients, in the right hand side x has to be changed to z. So, we have 2 sin z because z is equal to x square. So, particular integral will be 1 by d square minus 1, d here represents d over dz. So, 1 over d square minus 1 operating on 2 sin z, and this will be equal to 2 times 1 over d square minus 1 operating on sin z. So, when 1 over d square plus alpha square operates on sin z, we replace d square by minus a square. So, this will be 2 times 1 over minus 1 square minus 1 sin z. This is minus sin z. Okay, so we have got the particular solution as minus sin x square. So, thus the general solution is general solution is by equal to C1 e to the power x square plus C2 e to the power minus x square minus sin x square. So, that is how we solve this equation given in example 2. We have seen in the past 3 lectures we have seen how we can solve a linear differential equation of second order with variable coefficients when it is given in a, when we are given some special kinds of such equations. As I said earlier, such a general solution is not available for all second order linear differential equation with variable coefficients. Only a special class of such equations can be solved. So, we have seen those equations which can be solved in our past 3 lectures. Now, in my next lecture we shall be discussing how to find the general solution of a higher order homogeneous linear differential equation with constant coefficients. Thank you for your attention.